Okay. Yeah, I'm Michael. I'm from Quebec Lab of Washington University in St. Louis. As a side note, I'm not a neuroscientist, so every neuroscience terms that I might use here, they might not be super accurate. So I'm an electrical engineer by training, so I apologize already for any like wrong terms that I might want to use here. So I want to talk a bit about the behavioral description language that we want to kind of establish, and kind of happy that there was a bit of time here at the NWB workshop to basically present our current state of it. As Oliver mentioned already yesterday in his introduction talk, we are facing basically similar problems. So we have different ways of describing behavioral tasks that can vary from like cartoon-like graphics, like flow charts, similar cartoons, like abstract flow charts, description of individual trials, line charts kind of here, source code, and of course like plain text. So, and how to communicate those tasks depends highly on, like, of course, what type of task it is, what type of behavior task it is, but getting the most information out of each kind of like way of describing it is completely different, and it's not really increasing reproducibility. And so our goal is basically to find a way of like standardizing behavioral tasks, to communicate it, describe it, but also to reproduce it. Also in our task, in our lab, we have different ways of describing tasks. Like one of the latest papers from our lab, we have like this cartoon-like flow chart here that describes the confidence reporting task that basically everybody in our lab is using, everybody in our lab who is working with RED is basically using, where the animal has to perform a specific like time investment, reporting its confidence towards a given stimulus, and then if it was basically correct, will be rewarded, otherwise will not receive a reward and will basically lose the time it invested here. But as you can see, there are so many details in here that might be important for making it like reproducing the task again, and also for communicating it, that yeah, we are already in our lab having the problem on how to communicate it in a lab meeting if you make tiny differences in here. Yeah, it's not really like helping the community at all if details are missing in terms of reproducibility and yeah, trying to adopt paradigms from other labs. And that's why we already started way back. Marion, former lab member, came up with the idea of like block structures where all the modalities are basically laid out. But as you can see, it's already we have two different versions of it of the same confidence reporting task, but it's not really clear in what type of details are included. And I mean, as you can see, you can hardly read it. So making a step back again, what's actually the point of behavioral neuroscience? We have some kind of systems that are controlling an environment. We have like subjects, in our case it's rodents, but it can also be like monkeys, humans, whatever, that are presented specific stimuli. They are responding with some kind of action, some kind of like behavioral output, and we want to store this. And what we actually want to do is we want to program specific contingencies that describe the task, seeing the reaction of the subjects, and trying from the reaction of the subject, trying to infer the brain algorithms. And with BEADL, we try to have basically a big impact on how we can describe this program contingencies. So the overall goal for this project is actually having a sufficiently expressive way of describing all behavioral tasks. Of course, all behavioral tasks across all different subject types is a pretty big goal. But also being able to describe real-time events or real-time contingencies and also being able to like having a rigid formal way of describing it, making it therefore not easier, but making it straightforward to translate it to some kind of machine code, to run it on the behavior control system. And increasing reproducibility already within the lab, but also, of course, across lab, and having a standardized data format here with a newly introduced NWB extension that Oliver will talk about at the end of the talk. So with BEADL, we have split it up in 3 different sections. So we have a kind of design software that we're going to see later. We have also the kind of compiler on how to translate that for, in our case, the B-port hardware. And then the output of this task then being stored in the NWB data format. That's a bigger picture of it. So basically we have our description can be either the graphical representation of the BEADL designer, and this generates an XML file, but we can also write the XML file by ourselves, parsing it into, in our case, MATLAB, but we also want to introduce it also for Python and whatever the community actually needs. And for now, we need a bit of knowledge about the associated hardware to generate basically the underlying BEADL object, and then from that, then generating the code, getting the data back, and with the knowledge of how the task was being set up and what objects were basically being used, we can store it in an NWB compatible format, and then it can be transferred into an NWB container. I'm going to talk a bit about this BEADL graphs that we specified before we actually started with the XML approach, and we'll just briefly introduce how, what formal steps are involved here in the conversion towards the hardware. Then I'm going to show you the online BEADL editor, and at the end, as I mentioned, Oliver will briefly show the NWB extension. Okay, BEADL uses a finite state machine approach on how to describe behavior task, and we extended it because the formal way of defining a finite state machine might be too limited. More precisely, we're using a Moore machine as a state machine, which basically means the output action. So whenever the system, the behavior control system, is reacting with an output, this depends only on the state where the system is currently in, not on the event. There's also computer science basic, a mealy machine where the output actions depend only on the events. But then we actually have to see in which state we were, and it's not efficient for implementing it on hardware. So that's why BEADL also uses this kind of approach. And yeah, we have a different set. We have a set of different states the system can be in, or the control system can be in, where the subject is basically finding its path through. We have a set of events that can happen, basically the behavioral output of the animal. We have defined set of actions of the behavior control system, creating a stimulus, moving things around, whatever. And we have a specific state where the trial starts, and transition functions. So whenever we are in a state, we have a specific event we're transitioning to another state. And the output function here is basically only depends on the state. So whenever we enter a state, we are performing the output actions that are defined for this specific state. So that's the underlying concept. And a standard finite state machine approach would be kind of too limited. And we're going to see it already in the next slide. So 2 ways on how this can be implemented on hardware. Just theoretically, as a directly approach, the state diagram could be implemented as a switch case. We can also be transferred into a state transition matrix, basically a 2-dimensional array, where we have the IDs of the different states as rows, and the events as columns, and wherever there's basically a cross section between an event that we're currently in and a state that we are currently in and an event that can happen, we see in which state we're going to transition. So if we're in state S0 and we have E1, we basically stay in S0, or making a transition to S0 again. Whereas if we are in S0 and we have E2 as an event, we are making the transition to S1. So and that's basically also how most real-time state machine approaches are basically being implemented. This basically holds stored in memory, and it's pretty fast. You can also implement this with reconfigurable digital logic like FPGAs. Then this would be kind of faster. But if you have like a standard microcontroller, people are using, for example, Arduinos for that, that would be the way to go here. Because it's kind of like the footprint in memory is kind of small, and the execution speed here is basically 1 clock cycle. As I mentioned before, the approach of the standard finite state machine is a bit limited. So we want to extend it by knowing already that this might break the concept of making it available on all different behavior control systems. But I just want to point out one of the drawbacks of a standard state machine approach. If we are in a state 0, for example, here, and we have 3 different events that can happen, and we want to later in the state machine refer to which event happened earlier in the state machine, we would actually have to branch from here over to the systems at the bottom. So there's no real way of storing of memory in the state machine other than the path itself. So we try to adapt that with so-called virtual actions, so we can define variables in the state machine where we can store specific values in there. And later on in the associated events, then we take back this variable that we had, or the value that we stored before, and refer to it. This is basically not directly implemented in any state machine approach. We also defined callback functions, so we can basically break out of our system as long as the control system supports that, basically making a function call from an external system. So that's like what we defined as virtual actions. Virtual events can also be so-called argument events, so we can define values outside of the try description. I'm going to show that later, and depending on these values that are basically chosen on a try-by-try basis, make decisions in the state machine itself. And also in some cases, in some experiments, we want to basically get timestamps or durations between different states, and we implemented that also as well. And in standard state machine approach, this would also not be directly implemented. Okay, that's the underlying concept of BEADL. And when we started with that, taking from a lab member's approach, how we can actually draw that, we started basically by grouping everything together. That's basically one state, and writing it into one block. So we have the standard definition of the state in BEADL that has a name, and we can specify a duration. So we can specify how long the state could last, and until the system itself makes a transition to the next state. For example, we want to present the stimulus only for a given amount of time, and when this expires, we're basically going into the next state, waiting for the animal's behavioral feedback. We have a list of actions that we want to perform only in the state, and we have a list of events that can happen. You can see here we have also defined for events a so-called grace period. So we can define how long a certain event has to be minimally presented. With rats, for example, if they have to hold their head still for a given period of time if they're not head fixed, they're not really good in doing that, so they tend to move their head back and forth a bit. And you're going to see in one or two slides how behavior setup in our lab is basically looking. They have to basically put the head into port, and since they're not good in holding the head still, this might actually cause multiple events happening, so we would make transitions unintentionally. So we can specify a period of time as well as a minimum duration. So this is basically the minimum concept of the graphical stuff. And as an example, I want to show the very simple example, the light chasing task. So we have the subject is sitting in front of 3 ports. A port consists of a white LED, a photo gate detecting when the animal is poking its head in, and a reward system based on a bath in the water reservoir to deliver a drop of water. So the animal has to poke its head into the port where the light is being turned on, and this would be basically cartoon-like drawing of it. The equivalent BEADL task would look basically like this and also already reflect a bit more of details. You have a state wait for poke that has a duration that is infinite, and we're turning on the LED in the correct port that is chosen on a random basis. When the animal is poking into this port, we're in the reward state. We deliver the reward based on a reward draw for a specific amount of time. If the animal makes a mistake, we're going into a timeout. So the animal has to wait on this port and nothing is called. The animal has to wait for basically an extended period of time. And afterwards, we're going into an standard intertrial interval for also a predefined amount of time. That was actually, we're not using red in this example, but a mouse, and just to show you how that looks like, the red setups in our lab look pretty much the same. And it's not playing, that's great. Yeah. Yeah. Don't know why it's not showing up here. So, but you can see inside this picture now. We have 3 ports. Each one has an LED sitting on top. The light goes on. The animal has to poke in, collects the reward, has to wait for 6 seconds until it was correct. If it was incorrect, there was like a timeout period of another 6 seconds in here. Okay. So this reflects the logical structure, but also to reflect how the task is being set up on the task control system. We have to define additional values. So first of all, everything that's written in this purple colors here are so-called try-dependent variables that are defined outside the actual try. So we are selecting the correct port on a random basis. We define how much rewards should the animal get, how much should that reflect the time value, the bar needs to be open, and this durations. And the 3 sections underneath are actually defining the hardware. So what we try to do is here, it's basically whatever correct port valve means is just to specify here that underneath reflects the logical or the hardware connection. So if you have a different hardware, you could still name it the same way. You basically have to replace whatever hardware you're going to use here. But the overall structure would then be the same. That's a goal that we don't see too much on the technical implementations, like hardware implementations in the drawing. And as I said, we started first with an XML approach. I'm not going to go into details, but every section here that we have on the right side is in its own dedicated XML section. And we're going to implement this task in a minute. After defining basically the hardware components for the trial structure, we have state definitions in also each block, and as you can see, the correspondence between all the elements that are written in here. We have the name, we have the duration, we have the list of actions, we have the list of events. The only thing that is not shown in here, so here we can see 4 states. The definition, we have 5 states. We have 1 default state that also defines the end. In the beginning, we actually have to also say which is the start state. So I forgot about that. So we start with wait for poke, and once we reach the ITI and this kind of drawing, we're jumping back to the wait for poke state. But in the BEADL representation, the XML representation, we have to define also 1 end state. So that comes additional to it. But this will be automatically generated in the BEADL editor. Once we have all the states defined, with the corresponding events, we also have a list of the arcs here, the arrows, one from one state to another, given which event happened. So this is basically all that's being stored in the XML file, and current hardware setup that we have, we can actually run this. It's still kind of limited. Not all the features are implemented, and of course not the virtual events, because our hardware does not actually support them. But we didn't want to focus us too much only on our hardware. We wanted to have the concept of these virtual events as an extension to the BEADL framework. So this is an idea. We're parsing the XML file, mapping it on corresponding objects. That's currently changed how we do that. And afterwards, we can basically generate the protocol, the machine code. And there are specific sections in the generated code that the user can then still add custom code. For example, for this try-dependent variables that can be defined outside the try structure, let's say we want to have like a specific distribution for waiting times that we cannot really describe in a mathematical compact way, and we have to call specific functions for that. And for example, here in MATLAB, that the user can still add them. Of course, this breaks a bit the concept of having a general framework that is precise enough to define all the properties of a behavioral task. But that's the limitation that we have at the moment. So basically, we have systems in the generated code where the user can add custom code. And if we want the code's generation again, this code will, because we changed the XML structure, these sections will be preserved. So the user does not have to enter that again. That's basically common standard if you're coming from MATLAB or Simulink and generate automatic code to specific target hardware. That's basically the same approach. So we just adopted from that. Okay, coming now to the graphical part, where hopefully everybody who wanted to get a account got one already. So we have this web application based on a Node.js JavaScript framework where we can set up individual user accounts, and every user has its own workspace. We try to have like a kind of easy to use graphical editor. We know that there are definitely still limitations in there, and that we need to do a better job also making the drawings a bit nicer. But for the first step, that's what we ended up doing here. And we have different sections in the editor where we can define the try-dependent parameters that I described earlier, and also how we abstract the control hardware. Once we have the layout completely defined, we can export this to an XML description and then putting it into our code generating pipeline. Okay, let's see if I can directly switch over now. So if you log in with your account, you might see this BEADL user workspace. In your case, it might be empty. And once you have set of tasks defined, they're going to show up here. So I have a few just imported this morning into my account again, and we're going to redefine this light chasing task. So we're creating a new task, just giving it a name, and opening it up. First, we have to define which type of behavioral control hardware we want to use. That's funny that it looks so different. Okay, I hope you can see that. Let me lower the resolution. I think the resolution is simply too high. looks a bit odd, but yeah, okay. Never mind. Let's just jump into it. So let's say we all are using BPOD. We have to first select the hardware, but the idea is that the user can actually, with a exchange format, also populate their own hardware. And also, we want to extend the framework to also have like a generic BEADL set of input and output as generic types. So we can define, as I mentioned, these tri-dependent variables. For example, let's say we have a variable that defines which one is the correct port number. These fields for the code generation will actually be populated, and the user can basically, if this text field is empty, then enter its own values, or we can already write the code that should be used here. Since we're using BPOD with MATLAB, that would be the valid syntax for rand I5 for getting a... Let me just try to adjust the resolution again. You cannot read that. I'm sorry for that. Yeah, that looks better. Okay. We can also specify a comment that's also being then populated as a descriptor for in the code generation. And we can define the data type here. And the next step, we can define which kind of hardware we actually want to use or which components of the hardware we want to use. Let's say we want to define this correct port that we have seen in the drawing earlier, and it's behavioral port, as I mentioned. And we are connecting it to port 1. And let's already define the two other ones, the error port 1 and error 2. It's giving it arbitrary port numbers. So now we have basically the physical connection defined, what is the correct port and where it's connected to. And now we can define what type of actions do we want to have. So the correct port can use its LED. We're calling it correct port LED. And we want to use, for the reward, the Wulf instance of the port. So here you can see a behavioral port has an LED, a poke, and a Wulf. This is data specific for the hardware that's being stored in the database. And we are currently also working on an import format, how you can basically adapt to this kind of format with your own behavior control hardware, that you can import that you also can see the specific fields in the user front end. As events, we can have the correct port poke. I just name it this event like this, and I connect it to the correct port instance and the poke detection. And similar to the correct port, also defining the error port pokes. And now that I have actions and events defined, I can go to the graphical editor and create my first state, wait for poke. As I explained earlier, in the wait for poke state, we are just presenting the stimulus and we are just waiting for the animal to react to it. So there's no timer associated to this specific target, to this specific state. So as an output action, we want simply to turn on the LED. Also, these values come now from the database, but given the nature of BPOD, we could also use numerical values here. As input events, we want to sense the poke in event, so when the animal is actually putting its head into the behavior port. for the correct port and the two defined error ports. That's odd. Haha. Sorry. I forgot to select them. Okay. Yeah. So now we have the first state defined. And as I said, the end state will already be populated here as well. So we can zoom in this canvas, and now we can define the other states. So when the animal is making the right decision, we're going into the reward state. We want to just enter a numerical value in here now. I'm going to go back to that in a second. And once the animal is going into the reward state, we want to open the valve to deliver the reward. And since we now have specified a duration that is not infinite, we already have a so-called timer event. So when this duration is over, the state machine will also automatically generate this event, and we can make a transition. The state machine transitions out of the reward state into the next state that we want to basically use here. So the next state then would be the inter-trial interval, or ITI. I'm also just selecting now a numerical value. And in the ITI, nothing is happening other than we are waiting. So, and now I can start connecting things. So when the animal is going into the correct port, the system makes a transition into the reward state. We open up the valve, waiting in this case for 1 second, then going, leaving the state again, going into the ITI. I should connect it correctly. With a touchpad, it's tricky. And after the 6 seconds are over, we are making the transition into the end state. And if the animal is actually making a mistake, we are making the transition into the timeout state, where also nothing else is happening other than we are waiting. And I'm not good with touchpads, I'm sorry. Okay, so now we have basically the basic task layout defined here. As you can see, the connections are not super nicely laid out, so we're currently working on extending the JavaScript libraries for making this a little bit nicer, and also having the option for exporting these drawings from this canvas into an SVG graphics that you can then also use already in a publication style or publication ready format that you can order the different fields. Okay, so what's missing here right now is the definition of what is actually the correct port and what is the error port. Right now we have this connection basically fixed here, and for that we have so-called dependencies. We can define an argument dependency, and here we have a text field where we can actually use an expression that we, in the code generation, try to pass with regular expressions. So basically, we have the argument correct port num defined, and if this value is equal to 1, then we are using correct port. Then we are using the port 1 of bport as a correct port. Whereas if it is port 2, we would use port 2. We're currently also working on making these text fields highlighting the definitions of the argument arguments that we defined here, similar to, you might have seen that, this field. So right now, the duration that we want to specify for states will already populate the arguments that are being defined on the first tab for those values, because this is most often the case that you want to define the waiting times outside of the trial description itself, taking the history of the trial structure for adjusting those fields. And that's why we already populate those fields here that you can select them. And we're working on a way to automatically make this here a bit nicer, that you can specify this expression also in a straightforward way, that you don't have to enter it manually. But that's basically how we would then define the different ports. And since it's exclusive, the definition here, so it can either be 1, 2, or 3, depending on the argument that we defined over here. That's, of course, not programmatically, or the user interface does not know that yet. But using this approach, we can basically define entities with the same name, even though they are internally mapped to different physical entities. Of course, if I would make a mistake right now and would enter the 1 here, the underlying code generation would basically get confused and would throw an error message. But that's how for now, we define that. And if we generate the code now, let's say we want to run it 10 trials. Just store it here. Yeah, I trust myself. You can see that the code that's being generated is directly using the entities that were populated in the graphical environment. And here you can see the constraints that I just entered. And as I mentioned, the code generation is taking this expression and using a standard regex form to see if this can be mapped onto the defined arguments, and then on a trial-by-trial basis maps these entities to the corresponding hardware inputs or outputs. So that's the way the current state of BEADL is working, and what our goals are for the future, of course, making yeah, go ahead.
How complex can those expressions be? I mean, you're just showing an equals right now. Can it be like is not equals to? Can you use like an or an and condition?
No, I'm working on like using regex for that, and then basically branching. So right now I have just equal, smaller, larger, equal, smaller, equal, whatever. So, but it's basically argument value.
It's just a single expression.
It's just a single expression. So, but that's a current state. So, and we are working on making this a bit more straightforward, but that's the way we started for it. And as I can show you, we have, for example, our confidence reporting task also already in here. So it has a bit more complex arguments that are being defined outside. So with a beta distribution and some more complex fields here to take care of the different modalities of the trial structure. So this is basically the task that most people in our lab run with RADs. Right now, this is not being exported directly, so we haven't used this for the code generating yet because the RAD people are a little bit more sensitive to the task, and for now we have a bit of I still have a bit of problems with the generating of the code grace period for BPOT if there are specific entities being used in a task description using BPOT. But for example, as another approach, we have the detection confidence task. That is the complex ones that we have at the moment. Given the resolution of it, it's not showing up in Toad completely, but that's from the latest publication from our lab, the task. Also, we haven't used that with the code generation because it's hitting some limitations there, but conceptually that should work. I'm currently making this, the code generating, adapting to it, that it's actually producing the code. And as you can see, it's like 30 states or so. Looking at the source code with all the different transitions is kind of messy. Of course, it's already kind of messy also in this visual way. That's why we are hoping to have the transitions having the option of hiding the transitions just for the reducing the complexity of the visual representation here, and also making them a little bit nicer laid out. So that's what's currently working or currently being done on the front end as well. So that's the first step of BEADL. As I said, we are using BPOD here, but we don't want to limit us too much on it. That's why it would be great later this afternoon, if you're interested in giving me some feedback, what kind of hardware you use and what type of limitations you see trying to map BEADL onto your hardware setups, or the other way around. Okay, so that's, yeah.
So for really complex tasks like this, where you end up with 30 or more states, do you think it would be feasible to kind of create macro states?
We want to have group states, or nested states.
Yeah.
Similar, if people are using Bonsai for this describing behavior tasks or visual pipelines for task control, they can also nest parts of the algorithm. That's also what we want to have, that we can basically say, okay, this left section and the right section actually in this task is pretty similar. So why not just grouping them together? So having one nested group on the right side and one nested group on the left side. And as you mentioned, like template states or macro states that are performing the same type of behavioral actions that then will be basically reproduced. So that's also the idea. We are not there yet, and also how to just define that on the XML layer. But that's, yeah, these are currently ideas that we have. Yeah. And since we are already there, it's also time-wise that Oliver has like a few minutes to show the output.
Take as much time as you need. I mean, I will need, 5, maybe 10 minutes. We can always do that after lunch as well. And,
so
I can go over that after
okay.
lunch. And,
So, yeah, so what the stupid laser pointer. It's then already starting it. So what's currently on our immediate goals is basically increasing the usability. I mean, we already know that, especially with this argument definition, that this is not the smartest way to go. But given the point that we want to start somewhere, we just followed this approach. We want to have the export methods converting these graphs into SVG graphics and extending, of course, the supported hardwares. Yeah. Right now, of course, we're working still with BPOD, but going to the latest version, but also other hardware platforms. I don't know if you saw that, but we already integrated standard Arduino logic. So if we create a new, let's take the 10. If you select an Arduino here, under the resources, we see basically what an Arduino has. It has like digital IOs with PWM outputs, analog ins, a serial interface, and an I2C interface. So basically that you can theoretically generate a basic task just with an Arduino Uno. Of course, we don't have the code generation for that yet. Depends, of course, like a bit on how you want to lay out the created Arduino sketch, but theoretically it should be implementable. So that's what we meant with the kind of rigid framework that BEADL defines. That this should be given certain constraints, but this should be implementable on any kind of digital hardware. Yeah. And as I mentioned earlier, also with this virtual events and virtual actions, systems like Psych Toolbox that are just pure software, basically, that's not real-time system control, should also conceptually be able to be used here in BEADL, where we don't have like a hardware that we can select, but under the actions and events, I can call a callback function. If I give this a specific name, I don't know, in Psych Toolbox, whatever the function would be, I could basically use that here as well. So with these kind of mechanisms, I could basically call external code at some point. That's the idea behind it. Okay. Any other questions? As I said, I would be happy to get like feedback maybe this afternoon already from people if you have something that you want to share with me. Otherwise, you can try play around with it. You have accounts. If you have questions, feel free to reach out to me, and would be great to have some kind of feedback from the community, from you. What you think about it, what should be improved, what would be, from your point, like the major limitations, and maybe we can find a way of dealing with that. And I'm going to be around.